Eryk Kopczynski, paper with Anish Dawa on bounded degree and planar spectra.
Good afternoon. So what is the spectrum? It's a quite a classical notion from 52. We have some formula of, for example, first order logic over some signature, and the spectrum of this formula is the set of possible cardinalities of models of this formula. So, for example, if we take the conjunction of axioms of linear spaces over Z2, then it is a well-known fact that not every such linear space has two something elements. So the spectrum of such a formula is in the powers of 2. Another example is we take the axioms of fields, and then it is well known that each field has a cardinality which is a power of some prime. So here the spectrum is powers of primes, and there is a very good complexity theoretic characterization of spectra. So by Fegin, so a set of integers is a spectrum of some formula, if and only if the set of unary representations of elements of S is in NP. Equivalently, the set of binary representations of elements of S is NE. So this means that a set is a spectrum if and only if we can recognize its elements in pseudo polynomial time. So this polynomial, but not in the length of the binary representation, but in the length of the in the number itself. Let's look at the structure of the model, so applying from this Fegin's construction. So if we look at the Gaussian graph of this model, then it will be very complicated. It will be a clique, right? The Gaussian graph of a structure is the graph whose vertices are elements of the universe, and we have an edge whenever there is some tuple in some relation which includes both of these elements, and in the Fegin's construction we have a linear order. So this means that the Gaussian graph will be a clique. So our goal is to see what happens when we somehow restrict the possible models. So we somehow want our models to be simple, and such restriction can be phrased in terms of the graph theoretic properties of the Gaussian graph, like for example bounded treewidth or bounded degree or planar graph, and so on. And you would like to obtain a similar complexity theoretic characterization of spectra when models are required to have such properties. So there are some previous results in this area. So for example, if the signature includes only unary relations and one unary function, and then spectra can be only singular sets, which means that they are periodic starting from some offset. And this is mostly because if you have only one unary function, then the structure can be very simple. It can be some cycles and some trees, quite a simple structure. And this in fact even works if we take formulae from monadic second order logic instead of first order logic. Once we allow two unary function, then the spectra can already be non-next time complete. And this result can be this result about one unary function can be also extended to bounded treewidth. So in the previous case we had roughly trees, and if you have bounded treewidth, then we still get similar sets as spectra. And there is also a good survey from 3 years ago about the problems of spectra. So that's the prior results.
What is CMSO?
Monadic second order logic with counting. Modular counting, yes. So let's look at what happens when you have a bounded degree. So a degree D spectrum is a set which is a spectrum of some formula, which has a property such that all of its models have Gaussian graphs of degree at most D. Equivalently, you could say that a degree D spectrum is a set such that for some formula n is in this S, if and only if phi has a model with degree at most D, a model of size n with degree at most D. In case of bounded degree, these two definitions are equivalent because a first order formula can check whether the model has bounded degree, has degree D. And by BD spec, we denote the set of all degree D spectra. And our result is a complexity theoretic characterization of bounded degree spectra. And so it uses this class n times 2. So it is the class of sets of integers such that the membership can be recognized by a non-deterministic multi-tape Turing machine, accepting the binary representation of n as an input, and it has to run in time in the given time. And it should be noted that this time is this refers to the number itself, not the length of its representation. So this n times 2 of n could be called pseudolinear. And for this inclusion, it is enough to have degree 3, unary relation, and one symmetric relation, symmetric binary relation. So what technique is used can be used to show that this holds. So we are simulating Turing machines recognizing these binary representations and running in time n with bounded degree spectra. And the tool we are using is partial injective function symbols. If you have k of such partial injective functions, then this corresponds to having degree 2 times k. And we can axiomatize the following structure, where the universe is a set of numbers from 1 to n, and we have two functions, successor and doubling. And what we obtain this structure looks like this. Yes, this picture shows how this structure, what this structure looks like, and it can be axiomatized. And once we have this, we can add more functions. So you have some constant in the structure, and we can, for example, define addition of this constant. We can define multiplication by a constant, since we can add this constant many times. Since we have multiplication, we can calculate powers of 2. We can also calculate n divided by powers of 2, and and since we have this, we can use this L to find the binary representation of the size of the universe, and this H function here allows us to construct a grid. Right? We have arrows which goes to the next element, and an arrow which goes to the element plus C. This corresponds to a grid which has C columns and divided by C rows, and we can use this to simulate a Turing machine, non-deterministic Turing machine. This is not what this can be strengthened. We can use more sophisticated techniques to avoid this dividing by memory, and get linear time. So space is no longer irrelevant. This is done by somehow compressing the memory, so that if you are far away from the head, like in this case we are several steps from the head, then we use one element of the universe for corresponding to loss of time. In this picture, here is the tape, and here is time. And the other direction, we want to check whether some number is in the spectrum of some formula, which has a modulus of bounded degree. So we need to guess the structure of size n and model D and degree D, and then we can use Helm's locality theorem to effectively verify whether this structure satisfies our formula. This Helm's locality theorem says that for each first order formula there are some numbers R and M, such that we can check whether phi is satisfied in a graph by counting the number of R neighborhoods of each type up to the threshold of M, and this can be done in this time. So now what happens for planar graphs? And in case of planar spectra, there are two non-equivalent definitions. One definition is that a planar spectrum of a formula, planar spec, is the set of cardinalities of all models of phi whose Gleichmann graph is planar. So the formula can have non-planar models, but we don't count them into the spectrum. And P spec is the set of all planar spectra. Another approach is to have forced planar spectra, which means that we take a set of all a set is a forced planar spectra if there is a formula such that all models of phi are planar. And now the lower bound, we can use techniques similar as for bounded degree, but there are some differences. If you remember the picture of the Turing machine, then it was planar. So we can still try to do this. Previously, it was possible to do for a multi-tape Turing machine. But if you require a planar graph, then you can only allow one tape, which is denoted here by this superscript S. We no longer can read the size of the universe, because this spiral we have created it was planar, but we could not add much to it without losing planarity. But it is possible to calculate the size of the universe with a logarithmic overhead, and that's why we divide it by this log n here. Another approach here is to consider Q machines. So these are non-deterministic, non-contracting Q machines. So it is something like a Parsdown machine, but Parsdown automaton, but with a Q instead of a stack. So it has some states, and in each state it can read some symbol, and depending on the state and the symbol and some also non-determinism, it writes some symbols to the Q and moves to another state, or maybe accepts. And let's call QTL the class of sets of integers accepted by some Q machine, where we say that a machine accepts a number if it has a computation which writes exactly n symbols to the Q in total. And this has to be non-contracting, which means that it always writes at least one symbol when it reads one symbol. So here's an example of such a Q machine. The Q starts with a capital A, and the transitions are that a capital A can be changed. We can take a capital A from the top of the Q, and we can add capital A and small a to the end, and also we can double small a's. So this means that, and we can also accept the big A. So this means that in each iteration we can either accept or we can go through the whole Q and double it. And what we obtain here is that this Q machine accepts power of 2 minus 1. And this can be also done with a spectrum in a simple way. We simply write all the elements in the Q in a line, and use black arrows to show which element is next in the Q, and blue arrows to connect the position from which we are reading and to the position from which we are writing. And if we draw these Q machines from the example, we get the same picture again. These pairs of two should have a different color because they are capital A's instead of small a's. And it is of course known that Q machines are as powerful as Turing machines. In our case, this means that we can simulate Turing machines such that the product of time and space is linear. But now they can have many tapes, and so this is not comparable with the previous result. And as for upper bounds, from the our model, so our planar model so far have also bounded degree. So we can use again the same proof as previously. We only have to check whether the model is planar, which can be done. Also, without assuming bounded degree on it is known that on a non-deterministic RAM machine we can in linear time guess the model, verify whether it is planar and whether it satisfies this formula. So this also means that not every spectrum is a planar spectrum in this sense, because this can be done in polynomial time with a fixed power, and in general spectra can do polynomial with any power of n. So what happens when we want to force the planarity? So we want our formula to have a property that all of its models are planar, and our constructions from before do not work here. For example, our simulation of Turing machines, we can have a part which looks something like this, and once we there is this blue rectangle, we can draw this blue rectangle on a torus, and because it wraps around it nicely, and what we get, and we can add this torus to any model, and this breaks our construction because we get something like a similar set, because we can add as many of this story as you want. Also for the Q machines this doesn't work, because if you have a computation which turns W into W, then this also can be written on a torus. We could, on the other hand, simulate a Q machine which is extending. So each transition produces more, in some measure, extends the input. So the Q machine from the example had this property, and indeed we can our construction of the integers from 1 to n with doubling and successor can be done. This is a planar graph, and it has this is the only model of this formula. In general, the thing here, the problem here is that it has somehow allow this spiral. When we look at it in terms of Q machines, then we get only a logarithmic number of iterations, because each iteration blows up the Q exponentially. But we can still use this for some simulation of a Turing machine. So we are using the logarithm of n outermost layers of this spiral, and by using these outermost layers we can calculate the dr representation of n, and we can then run a Turing machine on this dr representation in space log d of n, and in time corresponding to the and in time which looks like this. So the result is that first planar spectra include Turing machine, non-deterministic Turing machines, which recognize the binary representation of n in logarithmic space and time n to 1 minus epsilon. So an example of an algorithm which has this property is the trivial algorithm of recognizing primes. We check all the numbers from 1 to square root of n, and this works in something like square root of n times log n time and logarithmic memory. So some possible areas for future work. So one question is whether we can reduce the gaps between our lower and upper bounds. So in case of bounded degree, its lower and upper bounds are very close. So I think maybe you should be happy that they are so close, because we have two very different models. So there is no good reason why they should be so close, but they turn out to be close. But the big gap is in the forced planar case, since we only allow logarithmic memory. So the question is whether it is possible to somehow use more memory. And then another question would be to see what happens for other classes of graphs with an excited minor. So that's all. Thank you.
Questions?
Can you go back on the inclusion for bounded degree spectra?
Yes.
Sorry. I'm not sure you. I think it's a hard problem to close the gap. Suppose you stop considering Turing machine, but you consider pointer machine in a kind of Kolmogorov-Uspensky, for example. So this time the storage is not a tape, but it's a graph with a bounded degree. And maybe it's possible that non-deterministic linear time on Kolmogorov-Uspensky machine is precisely bounded degree spectra. And these kind of machines are a priori more powerful, at least for real-time computation, than Turing machine. I'm not sure. But maybe if you want to have some equality, you have to have a model of computation which is less rigid than Turing machine in some sense, if you want to reverse the...
Yes, I don't know this model. So
you have Turing machine is a tape.
Yes.
RAMS is some kind of tape, but with a linear order. And in between, you have this kind of storage, little strange, which is a bounded degree graph. And then maybe it has some correspondence.
I mean, is there a reason to believe that every kind of one can throw a whole bunch of modular theoretic characterization? I mean, just even simple, triangle free. Is there a reason to think that each one would have some corresponding complexity theoretic, essentially analog?
I think yes, but it should have some complexity theoretic analog, because the lower bounds simply says that we can simulate some Turing machines with some time and space bounds in this class of spectra, and the upper bounds is the other direction. So it means that
no, but it just said that you can always have some lower bound, some upper bound.
Yes.
But if you want to get tight bounds,
yes, there is no reason why we should have.
I mean, it's just not clear to me that this is almost you'll have to find some kind of machine model that will correspond to the class of model you're considering, and at the end you'll be doing some overfitting, and your machine model will end up being somehow almost the logic, and then you have a tight sense. So it's almost lucky to have I think the characterization that you got, I'm speculating, but it's more just a few classes where you have a tight characterization. In general, I find it hard to believe that the Turing machine models and this model will give you exactly the same characterizations.
Yes, so
Other skeptics or believers? Okay, thank you again.